Hello everyone, I welcome all of you in the first lecture of our module Superposition of Harmonic Oscillation. Firstly, I am going to discuss about linearity and superposition principle, and then we will learn about superposition of two collinear harmonic oscillations having equal frequencies. Now let's move towards first point, linearity and superposition. We know that any motion which repeats itself in equal intervals of time is called a periodic motion. For example, the motion of pendulum in clock, the rotation of blades of fan, rotation of earth about its own axis. Simple harmonic motion is also a periodic motion. When the body performs simple harmonic motions, every particle of body oscillates along a certain path. If the path of body is a straight line, then the motion is called linear simple harmonic motion. If the path of body is a curve, then the motion is called angular simple harmonic motion. For small oscillations, we know that restoring force F is directly proportional to displacement y, and both are opposite in motion. That is, F is directly proportional to minus y. Then the equation of motion of oscillation is given by d square y divided by dt square is equal to minus omega square y, where omega is angular velocity. In the equation of motion of oscillation contains terms that only depend on y or d square y divided by dt square. Also, the power of y and its derivative d square y divided by dt square are same. Then such type of equation is called a linear differential equation. In 1801, the scientist Thomas Young stated the principle of superposition. This principle states that when two or more waves travel simultaneously in an elastic medium, then the resultant of waves is sum of the individual displacements. Let y1 and y2 be the two displacements which acting simultaneously on a particle. Then according to superposition principle, y is equal to y1 plus y2. To prove the superposition principle, consider non-linear differential equation is d square y divided by dt square is equal to minus omega square y plus a y square plus by cube plus equation number 1. Suppose y1 and y2 be the two solutions of equation 1, then for y1 equation 1 becomes d square y1 divided by dt square is equal to minus omega square y1 plus a y1 square plus by1 cube plus equation number 2. Then for y2 equation 1 becomes d square y2 divided by dt square is equal to minus omega square y2 plus a y2 square plus by2 cube plus equation number 3. Adding equations 2 and 3, we get d square y1 divided by dt square plus d square y2 divided by dt square minus omega square into bracket y1 plus y2 plus a into bracket y1 square plus y2 square plus b into bracket y1 cube plus y2 cube plus equation 4. If the principle of superposition is true, then y is equal to y1 plus y2 is also solution of the above equation 1. Then from equation 1 we write d square to y1 plus y2 divided by dt square is equal to minus omega square y1 plus y2 plus a y1 plus y2 bracket square plus b y1 plus y2 bracket cube plus equation number 5. If these two equations, that is 4 and 5, are identical if and only if all following conditions are satisfied. Condition first, d square y1 plus y2 divided by dt square is equal to d square y1 divided by dt square plus d square y2 divided by dt square. Second condition, minus omega square into bracket y1 plus y2 is equal to minus omega square into bracket y1 plus y2. Third condition, a into bracket y1 plus y2 bracket square is equal to a into bracket y1 square plus y2 square. And last condition, b y1 plus y2 bracket cube is equal to b into bracket y1 cube plus y2 cube. From this condition, it is seen that only conditions first and second are true, but condition 3 and 4 are true only if constant a and b are identical 0. In other words, our assumptions are y is equal to y1 plus y2 is the solution of equation 1 if non-linear terms a and b are absent. That is, we conclude that superposition of two solutions y is equal to y1 plus y2 is solution of only a linear equation. Thus, only linear differential equation d square y divided by dt square is equal to minus omega square y obeys the principle of superposition. Hence, resultant of two or more harmonic displacements is the algebraic sum of the individual displacement. We will discuss about second point, superposition of two collinear harmonic oscillations having equal frequencies by analytical method. Consider a single particle performing two or more simple harmonic motions simultaneously. The path, amplitude, and initial phases of simple harmonic motions may be different. The resultant motion of the particle is due to the combined effect of all simple harmonic motions. This phenomenon is known as composition or superposition of simple harmonic motions. Here, consider the superposition of two simple harmonic motions along the same straight line and having equal frequencies. Let y1 and y2 be the displacement of two harmonic motions having same angular frequency omega but different amplitudes a1, a2 and phase constant alpha 1, alpha 2 is y1 is equal to a1 sine into bracket omega t plus alpha 1 equation 1 and y2 is equal to a2 sine omega t plus alpha 2 equation 2. According to principle of superposition, resultant displacement y is equal to y1 plus y2. Then from equation 1 and 2 we write y is equal to 1 sine omega t plus alpha 1 plus a2 sine omega t plus alpha 2. Then by using identity, sine a plus b is equal to sine a cos b plus cos a sine b. Therefore, above equation can be written as y is equal to a1 sine omega t into bracket sine omega t cos alpha 1 plus cos omega t sine alpha 1 plus a2 into bracket sine omega t cos alpha 2 plus cos omega t sine alpha 2. Then rearranging these expressions, we get y is equal to a1 cos alpha 1 plus a2 cos alpha 2 outside of bracket sin omega t plus a1 sin alpha 1 plus a2 sin alpha 2 outside of bracket cos omega t. Here amplitudes a1, a2, phase constant alpha 1, alpha 2 are constant. Hence we can substitute a1 cos alpha 1 plus a2 cos alpha 2 is equal to capital A cos phi, equation 3, and a1 sin alpha 1 plus a2 sin alpha 2 is equal to capital A sin phi, equation number 4. Therefore, from equation 3 and 4, above equation becomes y is equal to a cos phi sin omega t plus a sin phi cos omega t. Therefore, by using the identity sin a plus b is equal to sin a cos b plus cos a sin b, the resultant amplitude of particle is y is equal to a sin omega t plus phi, equation number 5. Now, by using equation 3 and 4, squaring and adding equation 3 and 4, equation number 3 and equation number 4, squaring and adding, square of equation 3, equation 4, we write LHS a sin phi plus a cos phi bracket square is equal to a1 sin alpha 1 plus a2 sin alpha 2 bracket square plus a1 cos alpha 1 plus a2 cos alpha 2 bracket square. Square of this LHS RHS, we get a square sin square phi plus a square cos square phi is equal to square of first bracket of RHS term, first term, a1 square sin square alpha 1 plus a2 square sin square alpha 2 plus twice a1 a2 sin alpha 1 sin alpha 2 plus square of second bracket, we write a1 square cos square alpha 1 plus a2 square cos square alpha 2 plus twice a1 a2 cos alpha 1 cos alpha 2. Rearrange this expression, we write LHS as it is, a square sin square phi plus a square cos square phi is equal to, first bracket contains terms a1 square sin square alpha 1 plus a1 square cos square alpha 1. Second term contains a2 square sin square alpha 2 plus a2 square cos square alpha 2 plus last term twice a1 a2 into bracket sin alpha 1 sin alpha 2 plus cos alpha 1 cos alpha 2. Therefore, the resultant amplitude LHS a square is equal to RHS a1 square plus a2 square plus twice a1 a2 into cos alpha 1 minus alpha 2, equation number 6. Then dividing equation 4 by equation 3, we get phase constant, that is a sin phi divided by a cos phi is equal to a1 sin alpha 1 plus a2 sin alpha 2 divided by a1 cos alpha 1 plus a2 cos alpha 2. Then LHS becomes tan phi, RHS as it is, a1 sin alpha 1 plus a2 sin alpha 2 divided by a1 cos alpha 1 plus a2 cos alpha 2, equation number 7. Now we consider a special case. If simple harmonic motions are in phase, That is phase difference between them is 0. That is alpha 1 minus alpha 2 is equal to 0. And alpha 1 is equal to alpha 2 is equal to alpha. Then from equation 6 and from equation 7, we get from equation 6 a square is equal to a1 square plus a2 square plus twice a1 a2 cos alpha 1 minus alpha 2. We write a square is equal to a1 square plus a2 square plus twice a1 a2. That is a square is equal to a1 plus a2 bracket square. That is a is equal to a1 plus a2. And from equation 7, tan phi is equal to a1 sin alpha 1 plus a2 sin alpha 2 divided by a1 cos alpha 1 plus a2 cos alpha 2. We get tan phi is equal to a1 plus a2 sin alpha divided by a1 plus a2 cos alpha. That is tan phi is equal to tan alpha. Okay. Thank you everyone.